In Part 5, I discussed some very basic atomic theory as well as the mole concept. Solutions are critical in quantitative analysis. In this presentation, I will expand on the mole concept and introduce some very basic concepts in regards to solutions. I am Rob Boyko, Boyko Mineral Exploration, and welcome back. Not all acids or other compounds come as solutions. These solutions need to be prepared. Boric acid, carbonic acid, and citric acid are just a few examples. We also use solutions of potassium hydroxide, ammonium nitrate, potassium cyanide, and others. All of these compounds shown are solids, packaged as powders or crystals. To formulate a solution, the mole concept is used. The periodic table, on the bottom left corner of each element, is what is referred to as the atomic mass of that element. The molar weight, or M weight, is the total weight of each element in a compound's formula. In Group 9, atomic number 26, you will find iron on this table. Each item is listed with a single decimal point. The weights shown are rounded off and are given as grams. Iron has an atomic mass of 55.8 grams. This equates to 55.8 grams per mole. The table also shows that the most common elemental iron is iron 3 or ferric iron. It takes 2 iron atoms to combine with 3 oxygen atoms to make iron 3 trioxide. The molar mass or M weight of this compound is the total weight of each atom added together. Since there are 2 iron 3 atoms with a combined weight of 111.6 grams per mole, and 3 oxygen atoms at 16.0 grams per mole with a combined weight of 48 grams, the molar mass of this compound equates to 159.6 grams per mole. As mentioned earlier, we will have to create solutions that have specific concentrations of a compound or element. By dissolving the compound, such as salt, for example, until the solution is saturated, the solution can then said to be highly concentrated as a salt solution. The sodium and chlorine will dissociate into the solution as ions. These atoms are fairly compacted together in the solution. However, if additional water is added, the volume of the solution goes up. This disperses the ions within a larger volume. Concentration is based on the ratio between the number of molecules of solution and the number of solute ions in the solution. In other words, the number of moles or formal weights per liter of solution, as is usually given as a percentage. The solute in this example is the salt and the solution is the water. The concentration of the salt, therefore, will go down. Symbols are used to represent the weights and concentrations, including number of moles. The capital M represents the number of moles of solute in 1 liter of solution, and the capital F represents the number of formal weights of solute in 1 solution, whereas FWT is the formula weight of the compound. The lowercase n represents the number of moles of an element or compound. The respective equations are shown and will be discussed in the next few slides. Let's look at an example. Making a 500 ml, 5% saline solution. Calculating the amount of sodium chloride required can be calculated. First, the formula weight of sodium chloride will need to be calculated. By adding up the atomic weights, the formula weight is thus 58.5 grams per mole. The molarity of a 5% solution is 0.05 molar. Knowing what the molarity is, the moles of salt can be calculated, which is shown as 0.005 0.025 moles. From the number of moles required, the amount in grams can now be calculated. As shown, it is 1.4625 grams. If we had a scale that was calibrated to 6 decimal points, this amount could be weighed out with more precision and accuracy. However, if the scale was calibrated to only 2 decimal points, we would round off to 1.46 grams. To make this 500 ml solution, 1.46 grams of salt would be placed into a volumetric flask. 400 ml of distilled water would be added and mixed until all salt was dissolved, then topped up to the 500 ml calibration mark marked on the neck of the volumetric flask. Take note that 1 mole of sodium chloride is made up of 1 mole of sodium and 1 mole of chlorine, which dissociates as ions in water. Since formality represents the total amount of salt in the solution, the formality of the solution would also be 1.4625 F. I mentioned in a previous presentation, if buying chemicals, especially acids, as reagents, to purchase ACS grade and the highest concentration of the reagent as possible. Now this saves money as one can easily reduce the concentration of a solution. Reagent grades will be discussed later in a future presentation within this series. The method that is used is based on the equation C1V1 equals C2V2, where C is concentration and V is volume. Now it may look a little confusing, and in a way it is. The best way to show this is by example. A 3 molar solution of potassium cyanide is used. What is needed is a 0.1 molar solution for future experiments. All values must be the same on both sides. If V1 equals milliliters, then V2 must be in milliliters. Same with concentration. This is achieved by taking 50 ml of 3 molar potassium cyanide and pipetting it into a mixing flask of suitable size. A 200 ml flask is chosen. The calculation shows C1 and V1. In order to find the amount required for dilution, the molar value of C1 multiplied by the volume of V1 is calculated, then divided by the molar value that is required. As shown, this is 150 ml of distilled water. Since the initial amount was 50 ml, then 100 ml would be required to dilute the 3 molar solution. 100 ml of distilled water is then pipetted into the mixing flask and mixed thoroughly. The result should be 150 ml of 0.1 molar potassium cyanide. Note that any portion of the 150 ml of 0.1 potassium cyanide, that is C2V2, will have a concentration of 0.1 molar. Thus C2V2 will equal C1V1. Besides molarity and formality, there are more common terms used for describing the concentration of a solute in a solvent. In most cases, water is the solvent, and the compound is the solute dissolved in the water. Molality is the number of moles of solute dissolved in the number of kilograms of solvent. Note the weight is being kilograms. This calculation is always in kilograms or reference to kilograms. Similar to molality, percent weight or percent WW is calculated in grams multiplied by 100. It is a ratio between grams of solvent and 100 grams of solution. The solution is always calculated as grams. Percent volume is calculated in the same way. However, the solute is in milliliters. It is the ratio between the solute and 100 milliliters of solution multiplied by 100. The solution is always calculated as milliliters. Now, percent weight to volume, or percent WV, is quite common. It is the ratio between the weight of solute in grams and the volume of solution in milliliters. As shown in circled red on the label, this bottle of nitric acid is 20% WV. This too is always calculated as grams and milliliters. There are three more references of concentration that need to be presented: parts per million, parts per billion, and normality. Parts per million is based on grams and the metric ton. Sometimes it refers to solid materials such as elements and rocks and soils, including concentrates, but also the weight of solutions. As shown, 1 part per million equates to 1 gram per million grams of solution, or 1 milligram per liter, or 1 microgram per milliliter, or simply 1 gram per metric ton of ore. An example may be 250 parts per million gold, or parts per billion, which is similar as shown. Normality is different. It is based on the number of equivalences, which is based on the number of hydrogen atoms or hydroxide ions that can be donated that is released during a reaction. For example, hydrochloric acid has 1 hydrogen atom. The number of equivalences, therefore, is 1. Same with nitric acid. However, sulfuric acid has 2 hydrogen atoms. The number of equivalences in this case is 2, or N. Now the small n in this case means equivalence. It does not mean moles. In this case, 2 or N equals 2. Potassium hydroxide has only 1 hydroxide ion, and therefore its number of equivalences is 1. As a primer, redox equations will be discussed in a future presentation within this series, but the number of equivalences is the number of electrons donated. The redox equation shows that there are 5 electrons that can be donated. Therefore, N will equal 5. More on this, as I stated, will be presented in a future presentation. Now, normality of an acid or a base solution is equal to the number of equivalences multiplied by the molar concentration of the solution. 1 liter of 20% weight to volume, nitric acid for example, is equal to 200 grams per liter. 200 grams is equal to 3.1756 moles of nitric acid in a 1 liter solution. That equates to a molar value of 3.1746. The normality of the 1 liter of nitric acid, therefore, is 3.1746 times 1 equivalence, which is rounded off to 3.18 normal. Every substance has its own density. This is what allows olive oil to float on top of water, or sink, such as honey. It is basically the measurement of how compact the molecules of the material are within the makeup of its structure. It is a comparison of the weight of a substance and its volume. 1 cubic centimeter is equal to 1 milliliter of water. When dealing with solutions, the measurement for density would be weight per milliliter. For solids, it would be weight per centimeter cubed. Therefore, 20 grams of lead that had a cubic size of 2 cubic centimeters would have a density of 10 grams per cubic centimeter. And if that was dissolved, just for example, it would have a density of 10 grams per milliliter. The volume of a solid can easily be found by placing it into a volume of water. The amount of water it displaced would equal the volume of the substance. Not so easy for concentration of solutions. Using the density of a compound can be used to determine the molarity of a substance in a solution. A Google search will list a number of free density tables that one can download. Based on the constant of 100 grams, the 30% equates to 30 grams or 0.30. The density table will give us a density of 0.889 grams per milliliter, which, by the way, is temperature related. The mass weight is determined using the periodic table and the constant of 1,000 milliliters, which is used, as it represents a 1 liter solution. From the table, the density of the ammonia is 0.889 grams per milliliter, and in a 1 liter solution, that would be 889 grams per liter. The percentage on the bottle states 30%, which equates to 266.7 grams per liter. The mole weight is 17.4 grams per mole. Therefore, there is 15.3 moles of ammonia. In a 1 liter of water, the molarity would be therefore 15.3 moles per liter. This equation can be simplified as shown. Similar to density, all substances and compounds have a specific gravity or molar mass. It is formally known as relative density, which is a measure of the density or weight of a substance in comparison to the density or the weight of water. There are many instances where the concentration is presented as a percentage without a reference, such as volume to volume or weight to weight. As shown, this bottle of hydrochloric acid is 37%. In these cases, the molar concentration of a solution can be calculated by using its specific gravity. With a solid compound, the specific gravity can be easily determined as shown. Just weigh it. However, with solutions, not so easy. There are a number of specific gravity tables that can be downloaded for free. A simple Google search is all that is needed. A sample of a specific gravity table is shown. The molar concentration of this 37% hydrochloric acid solution can be determined just by assuming a 1 liter solution, which is 1,000 grams per kilogram, which is the weight of 1 liter of water. The percentage is always determined by assuming that the solute has a weight of 100 grams, which is a constant. Therefore, at 37%, from the table, the specific gravity of hydrochloric acid is 1.188 grams, which is then multiplied by 10 to the third grams, which equals 1,000, then further multiplied by the 37%, which equates to 37 grams, or 0.37, and finally multiplied by the mole weight of the compound. As shown, this equates to 12.04 moles of hydrochloric acid per liter, or simply 12.04 molar HCl. Now this equation can be simplified as shown. Now note the square brackets. It's just another way of stating that the value is the molarity of the substance. In this case, it's the molar concentration of the hydrochloric solution. Now this concludes part 6 of this series on classical assay for small-scale miners, prospectors, and hobbyists. In this presentation, I tried to discuss the creation of solutions as well as the reduction, that is, the dilution of solutions for required concentrations. That included the different terms that are used to describe the concentration of a substance in a solution and also how to determine the concentration of a solution. I tried to present this theory and math in a way that anyone may understand the concepts without a background in chemistry. In part 7 of this series, I will be discussing the decomposition of your samples. In regards to chemical analysis, all samples are dissolved in a solution as a first step. This is preparation. This is achieved by either dissolving in an acid medium or by fusion or by both. In Part 7, I will discuss the discussion on acids. If this interests you or know of someone who would benefit from this series, please give this part a like and a share, and if you know of someone who may benefit from this series, forward the link. I hope to see you in the next presentation. I am Rob Boyko, Boyko Mineral Exploration, and I thank you for watching.